Hello students, welcome back. Last lecture we have seen, we started with sampling theorem, where we have seen the statement of the sampling theorem and how it can be proved. So we have seen, we have taken one message signal and we have used one impulse train using which we are going to we have sampled the message signal and we have seen the resultant sample signal where we get samples of the original signal. And then we have seen all these signals in frequency domain also, how these signals look in frequency domain. And we have come to a final conclusion that if I see the frequency spectrum of the sample signal, we can see the replicas of the original message signal, right? So what is the conclusion from that sampling theorem? To reconstruct the message signal perfectly from this sample signal without any loss or distortion, there should not be any overlap between the replicas in the spectrum of the sample signal, right? So if there is no overlap, we can get the original signal's spectrum as it is. But if there is an overlap, we are not able to get back our original signal and there will be some distortion, right? So if we do not want it to happen any overlap in the spectrums, what is the condition that we need to satisfy? That the sampling frequency or sampling rate Fs should be greater than or equal to 2Fm, where we have seen that Fs is nothing but the sampling frequency or the sampling rate and Fm is nothing but the maximum frequency component present in your message signal. The same equation can be written in terms of the sampling interval also. So finding out sampling interval, we have to just take the reverse of this equation. So instead of Fs, I'll write 1 upon Fs, and this 1 upon Fs is nothing but Ts. And this condition also reverts, that is less than or equal to 2Fm. So this equation is called as sampling interval. So we have seen when we have taken a train of impulses, the sampling interval was that we have kept was Ts. So this sampling interval should be at least less than or equal to 1 upon 2Fm. So when this condition is satisfied, then only after passing the sample signal through a ideal low-pass filter, we can get back our original signal, otherwise not. Okay. So to get the original signal back in its original form, so that there is no overlap in the replicas and there is no loss of my message signal, what should be the minimum sampling rate? So when we are saying that it should be, Fs should be greater than or equal to 2Fm. So at least how much this should be? This should be at least equal to 2Fm. So when we say at least, that means it is the minimum sampling frequency, or you can say rate, with which I need to sample my signal. So this comes out to be Fs is equal to 2Fm. At least this much frequency we should use while sampling so that there is no overlap in the replicas. And this minimum requirement of the sampling rate is called as the Nyquist rate. This minimum requirement of sampling rate is given some name called as the Nyquist rate. So please remember, this is called as the Nyquist rate of the signal. Similarly, now if I am taking minimum of f of s, so there will be again a condition minimum of t of s. That is how much is the minimum sampling interval that we have to use, so that we can write ts should be equal to, so just we have to replace this less than or equal to side with equal to side, will be equal to 1 upon 2Fm. So this I will call it as sampling interval, Nyquist interval. So minimum sampling interval, which is called as the Nyquist interval. So always whenever you try to sample any signal, we need to first find out what is the Nyquist rate or what is the Nyquist interval of that signal, and then while sampling you should take care that at least you will use this particular rate, sampling rate for sample that signal, or this particular interval to sample that signal, so that there will be no overlapping of replicas of the frequency spectrum. Just remember, you will always come across these two terms, that is what is the Nyquist rate. So this Nyquist rate depends on what? The maximum frequency present in the signals. It is twice that of the maximum frequency present in the signal. And similarly, it is just, the interval is just 1/2 FM. So once these conditions are satisfied, then passing the sampled signal by using these conditions, if you try to pass this sampled signal through a low pass filter, we can get back our original message signal. So this process of reconstructing the original signal from the sampled signal, this process is called as interpolation. What is interpolation? Process of reconstructing original message signal from the sample signal. So we will come across this particular term also, what is interpolation. So this whole process of constructing the original signal back from the from the sample signal is called as interpolation. And for that you have to at least follow these two minimum criteria, that Fs should be equal to 2Fn and Ks should be equal to 1/2Fn. This is called as Nyquist rate and Nyquist interval. So in this process of interpolation, what we are using, we have some sample signal. Let's say we have named it as g of t in the last lecture. So this g of t has to be passed through a what? We are talking about a low pass filter. So an ideal low pass filter we are using. So when this g of t is passed to an ideal low pass filter, where this g of t is sampled at least with a Nyquist rate of Fs equal to 2Fm, then we can reconstruct our original signal back x of t. Obviously, we will not get x of t perfectly, so let's represent it that x bar t, which will be almost resembling your original signal, message signal, that is x of t. It is not exactly equal to x of t. So for this you are using an ideal low pass filter through which, so we have seen here, if I draw g of omega, that is this is the sample signal in time domain. So in frequency domain, if I draw it, we have seen that we will get a replicas of the spectrum like this, and these will not overlap if we are following the sampling theorem, and 0, and this will repeat at omega s. Right? If we are passing through this through an ideal low pass filter, what you should get back? You should get back only a single spectrum which is present about this 0, that is the middle spectrum which is present about this 0. So this is representing what? X of omega. So this is g of omega. This is x of omega. This is what we want it to happen, right? So this filter which is involved in this interpolation process is called as the interpolation filter. Okay, so this is a very important filter that we are going to use in this particular process, and now we are going to see that how this interpolation filter works. Now in frequency domain we have seen what we want. We have this as an input where we have replicas of the frequency spectrum of our original signal, and when it is passed through interpolation filter, which will be an ideal low pass filter. So I can represent this ideal low pass filter in frequency domain like this. So it should have a structure like this. Suppose this is a filter which I am representing by H. So this will be equal to H of omega. So this kind of response it should have, that this will only take the middle replica which is about origin at low frequency, and it should produce X of omega. This is what we want to happen. Okay. So how this filter does this? So let's see interpolation filter in detail. This we will require this particular, so interpolation filter. So what is this interpolation filter? This is nothing but an ideal low pass filter. So we are using an ideal low pass filter here, which can be used to reconstruct the original message signal from the sample signal. Now what are the requirements of this? What will be the requirements of this this interpolation filter? That its bandwidth should be FM, or it should have a cutoff frequency of FM, right? Because these replicas are present from what? Omega m to minus omega m, right? So if I want to have this whole replica, so my filter should at least have this much of width, right? So for this H of omega should be present, should have a bandwidth of what? The same thing, that is, it should be having from omega m to minus omega m. Then only it will be able to choose this particular part without any loss. And what else? This is the first requirement of the filter, that it should have a bandwidth of cutoff frequency of FM. Okay. What is another requirement of this interpolation filter? Another requirement of the interpolation filter is the gain of this interpolation filter. How much should be the gain? Now in the last lecture we have seen one equation of G of omega, right? This G of omega that we are passing through the low pass filter, we have seen the equation in terms of summation. If you recall, it is 1 upon Ts summation of X of omega minus omega 0. So this whole summation of X of omegas, it is multiplied by 1 upon Ts. Means it is been divided by 1 upon Ts. Okay. So to take care of this or to reverse this process, we need to have the gain of this filter as Ts, right? So when we multiply this, G of omega gets multiplied by H of omega with a gain of T of S. We can see this Ts and this Ts will get cancelled out, and then we'll get only this summation. So whatever effect of this Ts is making the division effect, that will be taken care of. So these are the two requirements of the interpolation filter, that the bandwidth should be equal to FM and the gain should be equal to at least Ts. So here the gain of this is Ts. So the height of this particular filter, if you see this in frequency domain, so it should be at least Ts, so that we will get back the original signal properly. So in frequency domain, after we have drawn, this is the filter. Now our emphasis is on this filter. So in the filter in frequency domain looks like this. So mathematically it can be represented as H of omega, represent H of omega, or let's say H of F right now, which will be equal to Ts, and we are using a pi equation, pi function, omega upon 4 pi Fn, which is represented as H of F, which is equal to Ts into pi of omega upon 4 fm, which can also be written as, if I represent omega as 2 pi f, if I replace this omega as 2 pi f, so this 2 pi and 4 pi will get cancelled out and we'll get what? Pi of f upon 2 fm. So in mathematically, this particular interpolation filter can be represented this way. You can replace f by omega also. Instead of f, you can write, we know that 2 pi f is omega, right? So omega upon 2 pi you can write here, and you will get an equation in terms of omega. Okay. So in frequency domain, we have seen how this filter looks like and how mathematically I can represent this. And in frequency domain, we have seen what would be my input and what is the expected output. But if I take the inverse of this, if I apply inverse Fourier transform on this, I wanted to see in time domain how this filter will look like. So I will try to find out h of t by taking inverse Fourier transform of this. So if I take inverse Fourier transform of this ts into pi function of f upon 2 fm, this is going to result into 2 times fm into ts, that is nothing but the sampling interval, and this is going to result into a function called as sinc function. Now you all know what is sinc function, right? So this is the equation of this interpolation filter in time domain. So it is 2 times the maximum frequency of your the message signal into the sampling interval that you are using, minimum sampling interval, and sinc function of 2 pi fmt. So this sinc function again depends on your message signal's maximum frequency. What is sinc function? We know that sinc is nothing but sine theta upon sec theta. So this function. So if I am having a frequency response or frequency spectrum of the filter like this, so in time domain it will result into a sinc function. Okay, so the sinc function, if I draw here h of t, this h of t with respect to t. So how that sinc function look like? At 0 it will have the maximum value like this, right? And then eventually it will become 0, it will just oscillate between positive and negative values, and eventually at t is equal to infinity it will become 0. Okay, so now this we have drawn for this particular frequency spectrum of the of this filter. So in frequency domain the filter will look like this. In time domain, if I see the response, it will look like this. So there are a few things which we have to note down here, as the bandwidth of this filter is omega m. Here in time domain we are drawing it, this particular intersection, wherever this sinc function intersects the reference line or zero line, it will not intersect anywhere, but it depends on what value of ts you are using. It depends on ts. So it uses the sampling interval. It crosses this reference line at every sampling interval ts, which is nothing but 1 upon 2n. So similarly here we get this as minus 1 upon 2 fm. So next will be 2 upon 2 fm, 3 upon 2 fm, and so on. So at every integral multiple of the sampling interval ts, this sinc function is going to cross the reference line. So if you have been asked the interpolation filter, what you need to do is, you need to first tell that the interpolation filter is nothing but what? An ideal low pass filter whose frequency response will be like this, that is h of omega. And there are two main requirements of this, that the cutoff frequency of the bandwidth is omega m and its gain is ts, and in the mathematical formula can be written like this. the same filter in time domain is represented by h of t, that is this equation, and in time domain the filter looks like this. Okay, that is nothing but a sinc function. So what actually is happening? Now we'll see. We have seen in frequency domain how what actually happening. I'm having this sampled signal where there are replicas, and then I'm multiplying this or passing through this filter h of omega. So this h of omega, what will it will do? It will select only this portion. This is what is expected. It will select only this particular replica, which is about 0, and it will give it back as the output. Let's see this process in time domain. In time domain, what will happen? In time domain, my g of omega will look like what? It is g of t, right? So it is sampled signal. I will see all the samples. Because this is g of t. So in g of t, what we'll see? We'll see the samples, right? Because samples like this. Okay, and all the samples are at what interval the samples are repeating? At sampling interval. So these are going to follow the sampling interval ts, 2ts, here minus ts, minus 2ts, and so on, both the sides. So I'm just taking one piece of the sample signal g of t. Now this g of t, we are passing through this particular filter h of t, and what we are expecting? We are expecting x of t. But as I have told you, we are not going to get back our original signal as it is. So let's represent this by x cap t, the reconstruction of x of t. So what is expected? When I am passing this sample signal through this particular filter, each of this sample g of t will get multiplied by this sinc function, and each sample will produce its own sinc function. And all these sinc functions will be different because, as you can see, the samples are having different strength. So according to the strength of the samples, each sample when multiplied by the sinc function will make some changes in the sinc function. The sinc function will be produced of that particular height, and then it will be produced, and then it will be given in the output. So right now we have not seen what should be the maximum value of h of t. So what should be the maximum value of h of t? We have seen one equation, I missed that part. So let me write down the equation again. We have seen this equation as 2fm ts, right? And the sinc function of 2 pi fmt, right? So this is the equation of this particular interpolation filter. So here, if I am assuming that I am using sampling interval matlab, or the Nyquist interval, better to say Nyquist interval. So Nyquist interval will say what? Ts, we know that sampling interval is Ts is less than or equal to 1 upon 2 fm. And when I say Nyquist interval, this less than or equal to sign is replaced by equal to sign. So if I am using the Nyquist interval, what I get? I will get Ts into 2 fm, right? So this replicates that 2 fm Ts is equal to what? 1, right? So this 2 fm Ts will become equal to 1, right? So for final equation of h of t will be what? I will replace this by 1, so it will be only sinc of 2 pi fmt. So what is its amplitude? We are multiplying it by 1. So this h of t will be having the height 1. Okay, so unit sinc function, unit value. Now let's go ahead with this. So as we were discussing, each of this sample will get multiplied by this sinc function. It will produce, because now the height is 1. So whatever height or whatever strength of this sample signal, the resultant sinc function will take that particular strength or height. So each sample, let's say, multiply with. This is very important and interesting to see how we are going to reconstruct our original signal band. So let's take this sample first. This gets multiplied by h of t. So this is going to produce at what instant? Minus 2 ts. This is going to produce a sinc function which is of this strength. Okay, so this is the sync function. That it will produce. Then at minus, again at minus, now where it is intersecting, we know that just now we have said the sync function intersects at what interval? At Ts. Let me just draw the size. This is our first one, and then I'll just mark these values, minus 2 Ts, then we have a interval at one sample at Ts, then at 0, then at Ts, then at 2 Ts, and 3 Ts, and so on. So we have all these samples, right? This is time axis, and this is what we are drawing is x cap. So this will be the same function for the first sample, like this, and it is going to intersect at every sampling interval. Okay, so this is the same function that the first sample will produce. Now the second sample is at minus Ts, having a little bit more height. How much? This much is the height. So this is going to produce its own sync function of this height, which will intersect here, right? Always the sync function will intersect here, like it will go like this. This is the sync function for the second sample. Let's see now for the third one. This is having a little bit more height. The sync function will go like this. And this side, like this. When you draw, you have to take care that the sync function crosses the zero axis only at the sampling interval. Let's draw this for the fourth sample. So the fourth sample will be somewhere here, and the sync function will go like this. Next is at 2 Ts. And one is there at 3 Ts, which is having a negative value. So this will come down, and the sync function will go like this. So we have taken total 6 samples. So every sample is going to produce one sync function here of the same height as that of the sampled signal. Okay. So this is what we get as the output of your ideal low pass filter. All the sync functions. Okay. Then from this, how I'm going to get my original signal back? What you have to do is, you have to just connect all these sample tops. From this only, if I integrate all these values, the maximum values, like this, now I may not be able to draw it properly here. Like this. If I connect all these sample tops, I may be able to reconstruct my original signal. Okay, so this is what is done. So what we are doing, every sample from the sample signal is passed through this low pass filter. So in time domain, as we have seen, each sample get multiplied by this sync function, and we get a train of sync functions here. And then to find the final signal, that is x of t, what you have to do is you have to add all these sync functions. Okay, so after adding all this sync function, you get this kind of output, which is nothing but your original signal, the reconstruction of the original signal. So mathematically, let's see how we represent it. Mathematically, this particular equation, this particular process is represented as x of t. So this is, I will have represented by x cap t, so I will write x cap t as what? Summation of all these sinc functions, right? So what we are doing is, we are taking the sample signals. So sample signals are represented in equation as g of k ts, right? So each sample at every instant of k, and this is multiplied. This is what we are doing. We are multiplying it by. We are actually not multiplying here. The things are convolved, right? In time domain, frequency domain, if they are multiplied, in time domain they are convolved. So we are taking convolution of it, and it is convolved with what? H of t. So this is simply the convolution equation, convolution formula, and summation. So we are summing all these. What this will result into? This h of t is what? The sinc functions, right? So the sample signals and the what your interpolation filter, and if you sum all these resultants, what you are going to get the original signal back. So if I replace here the sinc function, let's put this h of t as sinc function. So h of t is sinc, what? Sinc of, it is 2 pi fm t, right? So here t is replaced by t minus kts. So you get this, and finally I can write this as summation. This summation will go over k, for all values of k, g of kts, sinc of, we are just going to solve this bracket. So we get 2 pi fm t minus 2 pi fm kts. So what is 2 fm? Here I do not have place, I write here 2 pi fm multiplied by kts. But 2 fm, we know that what 2 fm is ts. So this gets cancelled. 1 upon 2 fm is ts. So finally what remains is pi and k. Okay. So this, we have represented the reconstructed signal in mathematical formula. How mathematically how we can represent this process of producing the sinc pulses and then finally finding out the result. So this is called as what? The interpolation formula. Okay. So now we'll stop here at this place, and next lecture we will see aliasing. Okay. So before that, I'll ask one question. If you have understood this properly, you will be able to answer it. So let's see. So this is one small problem that I have given based on what we have discussed till now. See how much, try to solve this and see how much you have understood from the last 2 lectures. Okay. If you are having, you try first. If you are having any doubt, you can just ask me the queries. Okay. So we'll stop here. Thank you.